A continuous study on work and energy. To record. Okay, yesterday we talked about how to calculate the kinetic energy for a rigid body. And for rigid body, the general plane motion, we know the kinetic energy will be two parts: translational kinetic energy and rotational kinetic energy. For translational kinetic energy, we just can calculate the kinetic energy like the rigid body is moving like a particle. So the translation kinetic energy will be this one, right? We're quite familiar. And Vg is actually the velocity of the mass center or the gravity center, because for us, generally speaking, if the rigid body is homogeneous, we mean that everywhere the material have the same density, the mass center, the centroid, the gravity center will be the same, right? Except not only the translational kinetic energy, and we also have the rotational kinetic energy. Rotational kinetic energy, when we um, try to memorize the rotational kinetic energy, never forget to match the variable for translation to the variable for rotational.
Ma'am, we can't hear you. The screen is blocked, teacher.
Can you hear me now?
知道老师。
Oh, thank you very much. So we need to start from the scratch, okay? Mm. Let's just wait. Okay. Yes, yeah. Finally, I need to start. Okay, from the beginning. Uh, okay, so now it's okay, right? You can hear me, right? No problem, right?
没问题，老师。
Okay, good. Okay. Okay, so let's start from the beginning. Okay. So yesterday we have talked about the kinetic energy for a rigid body. For a rigid body, we just have the translational kinetic energy and rotational kinetic energy. And for the translational kinetic energy, we know that for anybody is translating, it behaves like a particle. And so for a particle, for a translational body, its kinetic energy is 0.5 times the mass times the velocity square. And for the rotational kinetic energy, when you try to memorize the formula, never forget to match the variables for translational to the variables for rotational mass. Again and again, we know that mass is actually the inertia to resist the change in velocity, and the mass moment inertia is to resist the change in angular velocity, and Vg is for translation, omega is angular velocity. So just replace the variables of for translation to the variables for rotation. Okay, so if you can do this, it will be very easier to memorize the formulas in kinetics, because in kinetics we have a lot of formulas we need to memorize, need to understand, right? And so this is for general plane motion, and we all know that translation and pure translation, pure rotation actually are specific cases of the general plane motion. When the rigid body is doing pure translation, that means the angular velocity equal to zero, there will be no angular velocity. So for pure translation, the work, the kinetic energy will just like particle, right? Or we have tried to derive this yesterday, right? We know how to uh, we verify why when the rigid body is doing translation, the kinetic energy is exactly just like a particle, okay? And then when the rigid body is doing pure rotation, you still can use this formula to calculate the kinetic energy for rigid body which is rotating. We mean two parts: translational kinetic energy with the mass center and rotational kinetic energy around the mass center. However, we can simplify the kinetic energy for rigid body which is doing which is doing pure rotation as IO is actually the mass moment inertia about the rotation center. We just derive this, right? We verify, we use the parallel axis theorem to verify that you use this formula we just use plus the parallel axis. We just this one for pure rotation. They are actually equal to each other. Okay, so for us to calculate the kinetic energy for rigid body, it's very important to decide the motion of the kinetic energy to judge whether it is translating, rotating, or general plane motion. For this example, actually we know this system is doing rotation. And so to calculate its kinetic energy is actually to find out the mass moment inertia about the rotation center. And to calculate the mass moment inertia about the rotation center, we need to use the parallel axis theorem. And then for this example, you also did this question by yourself, right? And for this, we got two rigid bodies. Here, we need to add the kinetic energy of each body together. We calculate the kinetic energy of AB, we mean the AB and the disk. And so it's very important to decide the motion of the disk and the rod AB. For the disk, we know it's general motion because it's rotating without sleeping. And so its kinetic energy will include two parts. Translational kinetic energy with the mass center, rotation kinetic energy around the mass center. And for AB, we just found out that AB is doing instantaneous translation. It means that at this moment, AB, just the angular velocity of AB is equal to zero. And it behaves like it's translating. And so for AB, the kinetic energy is simplified to be the phi m times Vg squared. And Vg is equal to Vb, equal to Va, because we know for a translating rigid body, any point or any particle on the rigid body have the same velocity, same displacement, same acceleration, right? So you see, to calculate the kinetic energy is actually to figure out the kinematics. And why I just spend so much, I spend a lot of time on how to calculate the kinetic energy, because we know even for the work and the kinetic energy for a particle, we know the point is to calculate the kinetic energy correctly. The work of a force is easy to calculate for us for most time. And again, just like for a particle, here for rigid body, the definition of the work by a force on the rigid body is still the same, is to measure the effect of the force over the distance. Okay, so the work is the dot product between the force and the displacement. It's very important. It's a dot product. That means only the component along the displacement will do work to the rigid body. Okay, and again for the work, just for the weight, and the work done by the weight to the rigid body is again the same way we have calculated for the particle. It will be equal to the weight times the displacement. However, here the displacement will be the mass center, of the rigid body, okay, or the gravity center. Generally speaking, for us, if the material is homogeneous, we mean the density is equal to everywhere. The centroid, mass center, gravity center will be the same, will be coincident with each other. So here, for the rigid body, we need to know this delta y is actually the displacement of the gravity center. And again, and if the force and again, because the weight is downward, so if the rigid body is going up, the weight will do negative work on the rigid body, vice versa. Okay, so for the spring force, here we only talk about the linear spring. If it's not a linear spring, we need to do the integration of our work, but right here is a linear spring, and so based on the definition of the work, we do the integration, and then we calculate. The result is the force. The work of a spring force on the rigid body will be minus 0.5 k S2 square minus S1 square. Here it's very, very important. Here S2, S1 is measured. It's measured based on the unstretched position of spring. It's very, very important. Okay. S2, S1 is measured referring to the unstretched position. Okay, so this is the work by the spring force. So no matter the spring is pulled or pushed, or it's tensile or compressive forces to the rigid body, the spring force can do positive work or can do negative work to the rigid body, right? It depends on the spring length, the change of the spring length, right? Not only does we talk about the weight and the spring force, which how to calculate the work on the rigid body, and here we also need to be very careful. Sometimes the forces do not work on the rigid body. First, the internal forces between the internal forces between the rigid bodies will do no work, because as we have said again and again, internal forces always appear in pairs and always act in equal and opposite pairs. So the sum of the internal work the sum of the works by internal forces will be zero. They will cancel out each other. Except for the internal forces, some external forces sometimes also do no work to the rigid body. So, for instance, just like here, the normal force. The normal force when the disk is rolling, the normal force actually do no work to the rigid body. Why? Because we know the work is the dot product between the force and the displacement. If the displacement is always perpendicular to the force, even its external force, it will do no work to the rigid body. Okay. And here, the normal force, when the disk is rolling, the normal force will not do work. We should be very careful for friction forces. For friction forces, when the disk is rolling, if it's no sloping rolling. If it's no sloping rolling, or if the disk roll without sloping, what does that mean? It means the contact point, the velocity, the velocity will always, the contact point is the IC, right? Here is IC. So the velocity of the IC is always equal to zero. So this is a friction force. For the no sloping rolling, the velocity of IC equal to zero. We know the work is Fs dot ds. ds is displacement, and displacement is actually equal to the velocity delta t, right? And because v is always equal to zero, so the work by the friction force to the non-sloping rolling disk is equal to 0, or the friction force here do no work to the rolling disk. It's very, very important, okay, here. Even we have friction force, but because it's no sloping rolling, the contact point is the IC of the disk, or the contact point, the velocity of the contact point is always equal to 0, okay. Sure, if it's sloping rolling, the friction force will do work to the rigid body, okay. So just like a particle, the work of a cup, how to calculate the work of a couple, it's just like for a particle, we know the work of a couple should be equal to it should be equal to what? Can you tell me the work of a couple? Even I haven't seen it, but you should know this. This is the work by a force, right? Is equal to F dot ds, right? And so work by a couple and M, right? F replaced by M, so ds should replace by angular displacement, right? Or we may say this, okay? We may say this, okay? This is a couple, right? And so a couple is F dot ds. ds is equal to R d theta, right? Maybe we can use this, right? We can use this. But here you can use what I have said, just replace the F with M, so ds should be replaced with angular displacement. Sure, we can verify this. You can do the derivation, okay? When a body is subject to a couple, experience general plane motion. The two couple forces to work only when the body undergoes rotation, right? Because the couple forces, the resultant of the couple forces is equal to 0. So when it's translating, because of two forces are equal and opposite when it's translating, so the couple will do no work, right? Because they cancel out each other. That's why here we say the two couple forces only do work when the body undergoes rotation. So if the body rotates through an angular displacement d theta, the work of the couple moment m will be m d theta and integration from theta 1 to theta 2. Or you can see here, you can calculate for when it's rotation. When it's rotation, it will be F ds. And F ds and ds is equal to R d theta. And Fr is actually the moment, right? Here, when it's rotating, they will have the same direction of the work. Okay, so it will not cancel out. That's why we say for a couple, only when the body undergoes rotation, rotation can be pure rotation or general plane motion, okay? The couple do work to the rigid body, okay? And the work by the couple is equal to m d theta and integration. If the moment is a constant, that will be lucky. It will be simplified to the moment times d theta, okay? And when the moment and d theta are in the same direction, the work is positive, vice versa, okay? So after learning how to calculate the kinetic energy and the work by forces, you say the most important thing is to calculate the kinetic energy correctly. The work by forces are easy to calculate, right? By the weight, by the spring force, exactly like for a particle. You have learned that in middle school, and it's just a formula and it's easy to calculate. But sometimes some students will um, make errors for the spring force. Okay, so you need to tell yourself again and again when the work related to the spring force is very, very careful that the displacement should be measured from the stretched length of the spring. Okay. And then the work by a couple exactly like for a particle, right? MD theta. And then the principle of work and energy for a particle is the initial kinetic energy plus the work by all the forces equal to the final kinetic energy. And here, for the rigid body, it's the same. The initial kinetic energy for the rigid body plus the work by all the external forces will equal to the kinetic energy of the rigid body. Okay. So the work by all the forces, including the force and couple moments, okay? Here, the work, you need to calculate the work by all the external forces at the moment, okay? Here, never forget the work by the moment. The disk weighs 40 pounds and has a radius of gyration. Again, the radius of gyration is given. What does it mean? The radius of gyration is given, so the mass moment inertia is given because the mass moment inertia is equal to m kg squared, right? Is equal to the mass times radius of gyration square, okay? At 15 feet, one moment is applied and the spring has a spring constant of 10 pounds per feet. Okay, the moment here we got a constant moment and we have the spring and we need to find the angular velocity of the wheel when point G moves 0.5 feet. The wheel starts from west and rolls without slipping. You see, the wheel starts from rest. That means the initial kinetic energy is equal to zero. And the spring is initially unstretched. Okay, we need to find the angular velocity of the wheel when point G moves 0.5 feet. Here, you see, it's a period. Okay, it's not an instant problem. If it's an instant problem, we generally we need to apply the equation of motions. F equal to ma, m equal to oh. Do you still remember this? Actually, last week we talked about, even yesterday we had talked about this equation of motions. F equal to ma and m g equal to ig alpha or sigma mg or sigma mp equal to sigma mkp, right? Equation of motions. Yesterday, last week, we have talked about equations of motions. Equations of motions are generally used to find out the forces or the moments, okay? And it can only can apply to an instant, okay? However, principle of work and energy is actually an equation to describe what happened during a period. Okay, so if you find out the problem states that the rigid body gets from start from the west to or start from T1 to T2, this time you need to use the work and the kinetic energy. The principle of work and kinetic energy is also easy to apply. Why? Because we only concern about the initial state and the final state. We don't care what happened between them. And the work by the forces, again, is not difficult to calculate. So actually, after we have studied principle of work and energy, you just should have this impression that generally we apply the principle of work and energy to find out the velocity, acceleration, or angular velocity, angular acceleration. And then we apply equation of motions to find out the forces. We have done that before for a particle, right? For particles, we have just use the principle of work and energy and equation of motions to find out the unknowns, right? Here. So we need to find out the angular velocity of the wheel, and we know the wheel starts from rest. So initial kinetic energy is equal to 0. And how about the final kinetic energy? The final kinetic energy, we need to find out the angular velocity. The principle of work and energy is a scalar equation. One equation, one unknown. So T2, obviously, T2 is related to the angular velocity of the wheel. And we know to calculate the kinetic energy of the disk, we need to judge its motion. And it's given here. It rolls without slipping, right? It rolls without slipping. What does it mean? It means that the disk is doing general motion. The kinetic energy of this disk should include two parts: translational kinetic energy and rotational kinetic energy. And the translational kinetic energy will be 0.5 times mass times Vg. Vg is the mass center plus the translational kinetic energy, right? This is a mass. Here should be mass moment inertia. Here is the velocity. Here should be angular velocity. So here we have two unknowns, right? Because Ig is actually given because the radius of gyration is given. So we can find out Ig directly, right? And here we know that we got two unknowns. We got Vg, we got omega. So we need to find the relation, or we need to replace Vg with a function of angular velocity. But how to find out Vg, what's the relationship between Vg and omega? It's very important. It rolls without sleeping. Again and again, we have done this kind of practice, okay, without sleeping. So the contact point will be the IC. The contact point will be the IC, and so we will have the velocity of the mass center or the gravity center will equal to the radius to the IC times the angular velocity, right? So here, after we replace Vg with R omega, we know the here T2 will be only as a function of the angular velocity. So you see one unknown. Initial kinetic energy, final kinetic energy, initial kinetic energy, I should use T2. Kinetic energy is equal to 1, and final kinetic energy is expressed in terms of the angular velocity. We need to calculate the work by the forces, right? Before we calculate the work by the forces, we need to draw FBD, right? Only when you have the correct FBD, you can calculate the work by the forces correctly. The FBD, the weight, and the normal force, and the friction force, And here the friction force should be to the left or to the right. Can you tell me the friction force should be to the left or to the right? If there is no friction force, and under the action of the M and the spring force, the disc have the tendency to rotate clockwise, so the contact will have the tendency to move to the left, so the friction force should be to the right. This is friction force, okay? And we have the M, we have the spring force, and so the normal force do no work, right? Because the normal force will always perpendicular to the displacement. So the normal force do no work. The friction force, because it states that it's no slipping. So the contact point will be the IC. So the friction force will do no work. Okay, it's very important. Okay, so for the moment, we know the moment will do work. And the moment do work because the moment is a constant. So the work by the moment will be m d theta. And the spring force also will do work to the disk, right? How to calculate the work by the spring force? How to calculate the work by the spring force? The work by the spring force should be 0.5 and K is given, right? And should be minus S2 squared minus S1 squared, right? S2 is what? S2 is S1 is measured from the unstretched length. And here the spring is initially unstretched. That means S1 is actually equal to 0. But how about S2? And when you calculate the work by m d theta, we need to know d theta. What will be the d theta? Here, it states that when point G moves 0.5 feet, what does that mean? When point G moves 0.5 feet, that means the G moves 0.5 feet. What will be the relation between the displacement of the mass center G and the angular displacement? Can anybody tell me? Here is actually kinematics, right? You should find out the displacement SG and the angular displacement. What do we have? We have V equal to R omega, right? We have V equal to R omega. So V dt will equal to R omega dt, right? V dt, what will be V dt? V dt is actually the displacement of the mass center. Omega dt is actually the angular displacement, right? So the angular displacement will equal to the angular displacement. Here, angular displacement will equal to theta is equal to, let's say here, because here this is the radius, right? And the displacement of point G is 0.5. So the angular displacement, just as we have analyzed, the angular displacement should be 0.5 divided by the radius. I repeat, okay, here if we calculate the work by the moment, we know because moment is constant, it will equal to m d theta, moment times the angle displacement. We only know the ds. We only know the displacement of the gravity center or the mass center, and how to find d theta using ds. Never forget, it's no sloping volume, so we have Vg equal to r omega. Omega will be the angular velocity, and so times dt, Vg dt will be the displacement, and omega dt will be the angular displacement. That's why d theta equal to dsg over r. Okay, so except for the moment, we also have the kinetical. We have the spring force. This is the spring force, right? This is spring force. And here S1, because at the initial stage it's unstraight, so S1 equal to 0. But how about S2? S2, that means because here S2, we need to know this. So I think it's better to use this. Okay. So how to calculate the displacement of the spring force? How to calculate the S2? Because here this is Vg and Va. Again, because this is contact point, so at any moment, Va is always parallel Vg, is also horizontal, and Va is double to Vg, right? No matter when, no matter what time, the velocity of the point for the spring, contact point of the spring is always double the velocity of the mass center. Why? Because we know that the velocity of the point on the disk will be proportional to the distance to the IC. So VA equal to 2 VG. That's why the SA equal to 2 SG. Okay, that's why here is 1. Okay, so other forces, we have the weight. No, there is no displacement for the gravity center. So weight do not work. And the normal force, the displacement is always perpendicular to the normal force, no work. And FB, the friction force, again, the friction force here, because the contact point is IC, and the IC have 0 velocity, so IC do not work. Okay? So accordingly, after we calculate the kinetic energy already, we have already do this. Okay, already done this. Okay, then according to the work and energy, the initial kinetic energy plus the work by all the forces will equal to the final kinetic energy. So we can find out the angular velocity. Okay. So take 10 minutes break and then we continue our study. Okay, 10 minutes break.